Okay, so we have the problem, and I believe this is the problem that you sent me. We need we have this function f of x equal to x squared minus 7, and we want to find the line that is tangent to this this function, or this line, and is also parallel. Parallel to y equals negative 2x, I believe. So first of all, let's just let's attack this one step at a time. So we'll start with just the graph of the one function. Hopefully you can see this. So can you see that? Yeah. Okay. So we have this. We'll just draw a quick coordinate system. And so this, we'll just say this is negative 7, and this is going to be our parabola. It's going to look something like that. It's not a very good parabola. Just look at the right half. No, just kidding. So then we have this line that basically what it tells us is it's the slope. We're thinking about this slope. We have this line y equals negative 2x. We'll try to draw that in here. So this is negative 7. This is going to be negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7. So we have this line that's going to be about 1 over. It's going to go down. So this is the line that we have, and we want a line that's parallel to this, that's also tangent to this. So just eyeballing this, if I were just to move my ruler over, I'd see that, okay, a line that kind of runs right here, that should be about parallel and also tangent, so like touching like right at that point. So just right off the bat, it looks like something around probably negative 3 or something like that. But that's really a very informal way of going about doing this. So first of all, we'll just start with we'll ask ourselves, okay, so we need to find a line that's tangent to this guy. So we know it needs to be touching just at a single point, and it also needs to be parallel. So that means basically that slope, the slope, whatever line it needs to be parallel to this slope. So like a slope, like we have the line over here, and it's parallel to this line, but it's not tangent to this function that we have going right here. So we know that it needs to be actually on this function itself. So to start with, we'll just ask ourselves, okay, so what can I do math-wise to find the slope of this function at any given point? And just eyeballing this, then what I'm looking at is I'm seeing, okay, so the slope, like sort of like right here, that's really negative, like it's pointing really far down. So I know that it would be something that's like way down here. Like in terms of if we were to put it, like if we were to plot on the y-axis like the slope of this guy. So this is the function itself, but then this point represents the slope of this parabola at this given x right here. So we'll just, I don't know what this x is, or even what the slope technically is, but I'm just looking, I'm like, okay, so it's highly negative, so I know we're going to be highly negative. And then moving this way along the x-axis, then I look at, like, say this point right here, and I'm like, okay, this point, it's not quite as negative. Like, I mean, you can see that on the one hand, then we have the slope that's pointed way down like that, and then what we do is we move over and we're like, okay, so now the slope's more like that, and it's not quite like this one. You can see we'd have a slope of like maybe like negative 20, and then this slope's maybe more like negative 15. So that means that moving, so since we called this slope is negative 20, we'll just say it's negative 20. I can't say that's correct or anything, but just for example purposes. And then, like, say that this point it's like more like negative 15, or it's less negative. So I'm just going to move this one up a little bit and align it with like that point where I made that tangent. So it looks like I made it right about there. So I want to stick close to that, and so we'll say that's about negative 15, and then we'll kind of continue. We'll kind of continue making these slopes. Obviously, I'm not quite as precise as I should be. because this, yeah, it's about right there, and yeah, that's definitely not negative 15, but we're going to call it negative 15 for now, since we called this negative 15 at negative 15. So the slope corresponds to where it is on the y-axis, and again, the slope corresponds to where it is on the y-axis when we're deriving a function that describes this slope, that basically is this slope. So we want another function. We'll call it f prime of x, and it's gonna and we call it of x because for any given x, then we're gonna have a slightly different slope. So like for f prime of, like, say this, we'll say that was negative 3, negative 4, we'll say that's negative 5, then we're just gonna call that equal to negative 20. And I can't say that's correct, and actually it's not. Yeah, we'll actually call this more like negative 10. Okay. So let me erase all this. We'll say this slope's more of like negative 10, and this slope here at 4 is more like negative 8. And those numbers actually are correct. So let's see, it's negative 8, negative 9, negative 10, so negative 10. So the slope, like, we're going to call this a negative 5. Then we have this slope, we have this where we know the slope is negative 10 right at negative 5, or it looks like it. And so then the slope at negative 4, so f prime of negative 4, so like we're now in the negative 4 position along the x-axis, and we're just looking, we're like, okay, so the negative 4 position, we had this line that had a less negative slope, or closer to a positive slope, coming up right there, and that one is, we called that like negative 8. And so you see that, so we have this negative 4 going to about this negative 8 spot right here, and so that's right about there-ish. On this negative 3, then we have more like a slope of like negative 6, and so so if we were to keep plotting these points, we'd be like, okay, so we'll continue, like this isn't correct, this isn't to scale or anything like that. So yes, this is just a poor example, but basically we can continue mapping these slopes, and as you see, as we move along this function, then like the slope eventually, like this line, imagine my ruler is the slope of this line, it's coming right towards 0, so we know that right here at 0, then our slope's going to be 0. So we have this point right here, so we kind of have this line that's going up through the origin that kind of looks like this. And then like coming up on this side, you can see then that our slope's becoming more and more positive. So we kind of keep graphing it, and it kind of turns into this sort of a line. So it's like, so it's actually not a coincidence that it kind of looks like a line when we graph its slopes. That's just simply taking the derivative. And I don't know if you've gotten to the derivative yet, but I'm not even sure if this is how your teacher told you to go about taking this, calculating this line that's tangent and also parallel. But this is just the way that I would go about calculating it. If this isn't the correct way, then let me know, and I can definitely try a different way. But this is just the way that I would go about doing it. So first off, the derivative. So f prime of x, the definition of the derivative is the limit. Take the limit as x approaches. Okay, let's take the limit of f of x plus delta x, the change in x, minus f of x on top of x plus delta x minus x, and this equals this simply, and then as delta x approaches 0, because what we're doing is we're like, okay, so we have this this curve, right? And the idea is that we want to be like, okay, what point is tangent to it right there? And we can kind of get a good rough approximation by taking these 2 points and drawing the line that kind of goes through them, and then we can be like, okay, so we have a certain change in x and a certain change in y, but remember, our change in y, that's simply like our change in f of x, because f of x is really the same thing as y. Like for every x here